When we think of black holes, we automatically think of objects that are sucking in everything that comes near them, and that, once inside this object, there is no way out. And this rule even applies to the physical phenomenon with the highest possible speed in the universe, which is light. Because of this, we know that black holes are objects that do not emit light. Stars, for example, emit photons that are produced in their interior and escape to the surface. So, it may sound somewhat paradoxical when we say that black holes can shine. I just mentioned that it is an object that cannot emit light, but at the same time, I am saying that it is an object that can shine? Yes, that is exactly what you heard. Black holes shine, but not exactly for the reason you think. This was an effect discovered by physicist Stephen Hawking in the 1970s and ended up being named Hawking radiation. And you might have even wondered if this is somehow associated with the images we have of black holes with jets. But this goes much deeper.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
Hawking radiation can be a determining factor in how long the universe itself will last. It can also lead to the death of these objects that give the impression of being eternal. But before I can convince you, we need to make some points about black holes. I want to try to dispel that idea you probably have about black holes so that we can be on the same page. The first thing is, black holes are not exactly astronomical objects like stars are. You cannot compare a black hole with a star, or with a planet, or even with neutron stars. All these objects are composed of matter in one of its states, whether plasma, solid, or gaseous. And a black hole is not an object in that sense. It is more like a region of space-time with extreme curvature. Here's the thing. If you fell into a black hole, you would never see or feel that you entered it. You wouldn't see your feet, but you would continue to see the entire sky that you were seeing before entering the black hole. Of course, here I am ignoring the fact that you would fall into the singularity and disappear instantly. But the point I want to make is that the black hole is a region bounded by what we call the event horizon. And the event horizon is a boundary defined by the gravitational field, which is intense enough that nothing can escape. And of course, since the gravitational field influences radially, we observe a black hole as a dark sphere that does not emit light. And the reason why I want you to see a black hole as a region and not as an object is that this from now on will make all the difference. And this difference starts to become important for understanding the works of Stephen Hawking. Hawking may be one of the only people in history who can say that he found one of the pieces of quantum gravity. One of the only pieces found to date was in the 1970s. At that time, we did not have as many observations about quantum mechanics and relativity as we do today. But what led Hawking to find one of the only pieces of this puzzle? In the 20th century, two fields were born almost simultaneously: general relativity and quantum mechanics. On one hand, Albert Einstein introduced general relativity, which focuses on the description of the macro, where gravity is the dominant interaction. And he also explains how mass can distort space-time in a perceptible way. On the other hand, we had groups of physicists and chemists who were building the pillars of quantum mechanics, which is an area focused on the description of the micro and the interactions that dominate these microscopic scales, such as the electromagnetic, strong and weak interactions. And as a historical curiosity, Einstein is known for relativity, but his Nobel Prize can actually be attributed to quantum mechanics. But Einstein hated and despised quantum mechanics. One of the reasons Einstein hated quantum mechanics was that it was the first time in the history of physics that it delved deeply into the realm of probabilities. Hence the famous phrase he once said that God does not play dice with the universe. With the advent of quantum mechanics, things were no longer deterministic as they always had been, and strange phenomena were allowed, such as quantum entanglement, which Einstein himself described as something supernatural and nonsensical. However, quantum mechanics, like general relativity, has been successful in all the experiments and observations in which it has been tested. However, as you may know, there is a very serious problem here. Quantum mechanics can communicate with classical mechanics and electromagnetism, but it cannot communicate with general relativity. And in the universe, there existed something that required both areas together to be described, which are the singularities. Whether at the center of black holes or even at the origin of the Big Bang, it was the universe showing that there had to be a way to make quantum mechanics and general relativity communicate. Einstein himself spent the last decades of his life trying to unite these two forces. He was not successful. And it is in this context that Stephen Hawking emerges, who began working with general relativity, mainly black holes. And he was responsible for the second postulate of black hole dynamics, which stated that black holes never decrease in size. And shortly after he introduced this postulate, he also became interested in quantum mechanics and quantum gravity. He became interested in understanding how quantum mechanics operated in the environment around the black hole. And remember that I mentioned the event horizon is a region? This is exactly where it starts to become important. Hawking focused on studying how quantum effects occurred in this region determined by the event horizon. While he was working on this, he realized that there was something wrong with his postulate. His calculations indicated that black holes could shrink in size, and this effect became known as black hole evaporation. But that wasn't the only strange thing he found. He also realized that black holes could, for lack of a better word, shine, something that until then was thought to be impossible. When he introduced these ideas, at first they were considered quite controversial among physicists, and were met with a lot of criticism. But gradually, this idea received the due recognition and was considered one of the greatest advances in theoretical physics. The phenomenon discovered by Hawking was named Hawking radiation. But how exactly does Hawking radiation work? The first thing you have to keep in mind is that the vacuum is not exactly empty in the way we think. Quantum fields are distributed throughout space-time, including the vacuum. But what is a quantum field? Within quantum mechanics, each particle and interaction have an associated field, and these fields describe the distribution of energy or momentum for each particle. Imagine it like this. It is as if every point in all of space had values of energy and momentum for each particle or interaction. But since nothing in quantum mechanics is that simple, and we are talking about a field based on probabilities, of course, this is not the end of the story. According to the Heisenberg uncertainty principle, it is impossible to simultaneously reduce any of these properties in the quantum field. Some examples of such properties are position and momentum, or energy and time. And the more precise one property is, the more uncertain the other becomes. When we have a very small region and a very short time interval, it is impossible for the energy to become increasingly uncertain. And I'm not talking about measurement precision as if we were measuring. I'm talking about something inherent to nature, something that comes from the universe itself. And because of this, energy can oscillate at certain points, and we see this as vacuum quantum fluctuations. It is precisely a random change in energy. It turns out that a given point can have enough uncertain energy to produce pairs of particles, and these particles are called virtual particles. They are not observed directly, and the existence of these particles is extremely short enough for the system's energy to be conserved. But we know that this phenomenon occurs through observations and experiments, such as the Casimir effect. What I mean is, this happens throughout space-time. We basically live in a sea where particles are being generated and annihilated all the time. And what does this have to do with Hawking radiation? Well, if this is happening everywhere, then it also happens at the event horizon, which, as I have already mentioned, is a region of space-time. Generally, these particles annihilate quickly, but when they are at the edge of the black hole, something strange can happen. A particle can be created inside the event horizon, and another particle can be created outside the event horizon. Since nothing can escape from inside the black hole, the particle that was created within the event horizon cannot escape. Meanwhile, the other particle gains enough energy to escape the gravitational field, but this energy has to come from somewhere. And fortunately for us, we are talking about the edge of an extreme object. The particle escapes with the energy taken from the black hole itself. And at this point, you might be wondering, okay, but how does this make a black hole shine? Looking from outside this system, these particles are generally photons or low-mass particles such as neutrinos. And because they are photons with a specific frequency escaping from all directions, the black hole seems to be radiating or glowing. Hawking found a relationship between the frequency where these photons emit and the mass of the black hole. In this equation, T is the temperature that defines the curve in the blackbody electromagnetic spectrum, that is, how much it emits at each wavelength. And Rs is the Schwarzschild radius, which is defined solely by the mass of the black hole. From the temperature, Hawking calculated the amount of energy emitted per second, which is the luminosity, and it depends on the area of the black hole. And in turn, the area depends on the Schwarzschild radius, which depends on the mass of the black hole. In other words, Hawking radiation is directly related to the mass of a black hole. Using these equations, Hawking discovered that large black holes emit radiation at longer wavelengths and lower energies, and they emit extremely slowly. In other words, it would take billions of years to make any difference. And depending on the size, if black holes were very small, near atomic scales, they would evaporate in a short time. And I know that I haven't yet explained how they can die if they are only emitting light. The answer is simple, and it is an equation that I think you must have seen somewhere before. E equals mc squared, This equation shows that energy and mass are related. It is basically the same physical entity, except for a constant. When the black hole emits this radiation, it is losing energy, as the escaping particle steals energy from it. But since energy and mass are equivalent, the result is that the mass of the black hole also decreases. And if the radius depends on the mass, then the black hole will keep shrinking until it completely evaporates, reaching the end of its life. And this brings us to the next question. Are the black holes we see today dying? And the answer is yes and no. Hawking radiation is a phenomenon that is continuous and happens all the time. So yes, this is already happening in black holes at this very moment. However, a large part of the black holes we observe are feeding, even if very little, such as the one at the center of the Milky Way. The evaporation process is so slow that they consume more than they can lose through Hawking radiation. So the answer is also no, since they not only quickly replenish what they lost, but they also consume even more, increasing in mass and size. And for supermassive black holes, this is even more evident. The radiation is so weak that it doesn't even tickle. However, there is a situation where Hawking radiation can prevent accretion, making the evaporation process even faster. This would happen for extremely small black holes on atomic scales. Hawking radiation would be so intense in these cases that the radiation pressure caused by these photons would serve as a barrier. So without accreting and radiating intensely, the small black hole would die very quickly. But here I leave a note. These small black holes would have to be primordial black holes. And currently we do not know if they actually existed. But we can go a bit further in this story. At some point they will stop feeding while stars, galaxies and planets cease to exist. There will come a time when there will be no more gas and nothing else that can serve as a source for the accretion process of black holes. They will no longer be able to feed. At that point, nothing will compensate for the mass loss through Hawking radiation, which will just keep happening continuously, and finally, they will actually start to evaporate. And this is the era of black holes in the chronology of the universe. The process is so slow for supermassive black holes that this era could last until the universe is 10 to the power of 100 years old. That is a 10 followed by 100 zeros. On this timescale, we haven't even reached 0% of the age of the universe. It is curious to think that an imperceptible effect today will be a determining factor in the duration of the universe. Perhaps it is a good time to mention that the effects of Hawking radiation are so weak that we have not yet had any direct observations. The brightness of the accretion disk completely overshadows the Hawking radiation. It's the same as going to space, lighting a lamp next to the sun, returning to Earth, and trying to measure the lamp's luminosity and brightness while ignoring the sun. Spoiler, you won't be able to. But Pedro, how are you talking about all this when we don't even know if it happens? And this is where the beauty of science comes in. The first thing we need to keep in mind is to ask ourselves, does this model agree with the accepted concepts and laws of physics that have already been proven? And the answer is yes. In the case of Hawking radiation, it aligns with the established foundations of physics, and there is no impediment that prohibits its existence. The second thing is that we have been able to observe analogous effects in the laboratory. One example is the Casimir effect. It is based on the same idea of virtual particle creation. In 2019, a group of physicists published in the journal Nature that they managed to conduct an experiment with the Bose-Einstein condensate. And in the work, they analyzed the system in which the effect would be equivalent to Hawking radiation. And this is one of the experiments that prove the theoretical part of the phenomenon is correct. There are no reasons to doubt. But of course, when we talk about science, we talk about the scientific method. And if we talk about the scientific method, we are talking about observations of the phenomenon itself, and not just analogies. So, will it be possible to directly observe Hawking radiation someday? It may be possible, with the advancement of technology, to find isolated and inactive black holes, and extract some information from their Hawking radiation. But the bets are on primordial black holes. There are experiments that try to look for explosions in the sky that are primordial black holes at the end of their life. The last moments of a primordial black hole's life are a gigantic emission in gamma rays due to evaporation. And one of these experiments uses the HESS telescope. This is one of the experiments that are already underway searching for evidence of Hawking radiation. Hawking radiation remains one of the only pieces that manages to use quantum mechanics in a place where general relativity dominates. It is far from being able to explain the singularity, but it is a piece in the puzzle of quantum gravity. And if this is the best tool we have at the moment, it is the best chance we have to answer questions that even Einstein couldn't answer. Today we have technology that was not possible in the last century when so many physicists worked on this problem. We are the first generation to see a picture of a black hole. and it is possible that we will be the first generation to see the confirmation of Hawking radiation. But I think all of this is a stepping stone to an even more ambitious question. Will we be the first generation to witness the unification of physics? I would like to know what you think. I would also like to ask you to subscribe to the channel. It would greatly help the channel and my work. Thank you very much and see you next time.